Okay, hello, good morning. Welcome back to today's section of our lesson. We are still in modeling. You know, the last time we did something on modeling, that we talked about the types of modeling that we have. We made mention of independent model. We made mention of dependent variables, and so many types of variables. We also make mention of the random variables, among other components. Now today there's something I want us to look into, and it's called the exogenous variable. But before that, I would like us to take a look at what we did in our previous lesson. Okay, welcome back. Now when we talked about exogenous variable, we said that exogenous variable, we threw light on it, that they are independent variables that affect a model without being affected. Now, one of the things I want us to know is that exogenous variables act as catalysts among variables. They affect the variables, they affect the model, but they are not being affected. So they remain the same throughout the entire process, and whose qualitative characteristics and method of generation are not specified by the model builder. An exogenous variable is used for setting arbitrary external condition and not in achieving a more realistic model behavior. So an exogenous variable is just a variable that acts as a control. It's a variable that acts as a control. It acts as a control to other variables. For example, let's talk about a food that has been prepared in the morning. Okay, the food is X and is prepared at a particular time. Then without heating or applying any means of preservation, the food will decay at a particular time. Now if we want to get this, let's say this is it. Now let's check how it's been done. You know, in mass, if you want to check the rate of decay, we'll say the x over the t from this is equal to t, but we'll add our what? A constant to it. Now this is called the decay constant, while this is called the exogenous variable. Now in this, we discover that in trying to generate this equation, there are so many things that are being put into place. The variable is not altered, but at the same time it works as other variables, but instead it has an effect on the reaction we are being considered. Now let's use in solving this question from the explanation that we just saw in front. Let's call this example 1 for today's lesson. Now what we have here is, they said observations have shown that the rate of change of atmospheric pressure, given that the pressure at 6,000 meters, that's P at 6,000 meters above sea level, is half its value, which is P naught, at sea level. That's, if this is the value, then that's the value P is equal to half of this, so P is equal to this. Let's state our parameters clearly while we are still reading the question, so that we'll know what we are looking for. So that's to say the value of the atmospheric pressure at this point, at this level, is half that at the sea level. So find the formula for pressure at any height. We want to get the formula for pressure at any height, given that now a clue was given to us here, given that h is equal to the integral of k large change in h. Now let's work on this. Let's integrate this with respect. So you now have, since we are dealing with P, you now have the ln of P is equals KH plus C. Now you're integrating with respect to what? To H. So that's why you're having ln H. You remember how to do your integral, like if you have x, you have 2dx. So the integral becomes 2x plus k plus the constant term. So the same thing is applicable here. We have KH plus C, which happens to be the constant term. Now let's move further by expressing this. Now you know ln P means the natural logarithm of P. So we can still express it this way as P to being equal to exponential KH plus C. Now this has been transformed into this, because when you have this ln P and you have a straight number, in order for us to have P, we have the natural log, you call it the exponential of this. So with this, and according to our law of indices, we know that when we have 5 raised to power x plus 2 is the same thing as 5 raised to power x times 5 raised to power 2. So I would like us to apply this concept. Here. So this becomes P equals e raised to power KH times e raised to power C. Okay, from here, let's make A to be equals AC. We are trying to look for the relationship, because the question here says find the formula for the pressure at any height. So we are looking for the formula. So let's continue. So our expression now is P is equals E KH times A, which is AEKH. Now this is the value of P and H. But remember, they said above the sea level is half of PO at sea level. Now when you're talking about sea level, at that point, at sea level, H is usually equals 0, because no height has been attained. So let's replace this point with 0. So we now have it that our P is equals A e raised to power 0, which is A times 1, which is A. So you can see that our P is equal A at sea level. Now we move further into solving. Now using this relationship, remember the relationship we cited before now. So our value of P is 2 of these. So we now have P is equal P naught over 2. So from here, we now state clearly that if that's the case, then P naught over 2, which is our P, is equals P E 600 K. Remember that the value of H is equal to 6,000 meters, so 6,000 K. So from here, breaking further, we now have a half to be equals E raised to power 6,000 K. So cross multiplying by cross multiplication, we have that 1 is equals 2 e raised to power 600 K. Now, which happens to be the formula for height at any given pressure. And I think we've done justice to this. So I would like you to take this test that will be coming up in your screen. And do well to use the lesson notes on this platform for a better information on the topic we've discussed. Feel free to drop your questions on the comment section. Thank you.